afternoon again. See the how to just minimize this side. This one. This is better. Okay. So good afternoon. This is granular mining, uncertainty modeling, and video analytics. But you can use it to any kind of data. And I'll go from shallow to deep learning. That shallow word I coined in 2016 when one of our MTech students from Calcutta University did her dissertation. That's why we published a paper in neural network and application to that basic concept. Granulation, I will say what is granule? I tell you. See, I'm looking at the audience. I can see some old persons there, some young people there, some lady there. So without looking at the individual, I can see this is called granule. When I see a scenery, what I see? Water body, vegetation, sky, habitation. So these are my granules. So I will explain what is granular computing. That means you extract granules of a given environment, given data set, and you perform following operation based on the granular information. You forget about the data. That's all. Since you are performing based on compressed information, because granule is a kind of compressed information. So you gain in computation time. Therefore, it has significance. You can see application for handling large data. But now today, after 2010, we all talk about large data. Before that, we didn't say. After 2010, data mining, big data, now data science, everything. So I will explain the granular basic concept. I will explain one example, the rough set, which has maximum amount of contribution to the granule. The entropy, generalized entropy, which takes care of uncertainty, because any data, whether small, medium, or large, uncertainty is inevitable. You cannot remove, but you can reduce. You can handle. Uncertainty arises from probability of occurrence, uncertainty arising from overlapping concept, uncertainty arising from granularity. So I'll consider only two things: uncertainty arising from granularity in the domain, uncertainty arising from overlapping concept in complete, not probability of occurrence. That if you can bring it, it will be even stronger model of uncertainty management. The video analytics, object extraction, that's the important thing nowadays. I will take an example. Then I will some new concept we introduce, rough filter and other thing. Then granular deep learning, that's what you put in the last one. Why granular deep learning? Because deep learning is expensive. Deep learning depends on large number of data. Larger the number of samples, better is the learning prediction capability. So since you have a large number of data, it is time consuming. So how to reduce the time consuming? On the other hand, granulation, as I explained, it leads to computational gain. But nothing is free. You lose some information. And in our most of the data mining problem, we do not need the precise definition. We need approximate. But if you want to precise, then you start from the approximate, that pay you little more, and then you just find the one. So instead of starting from the scratch, you start from a better position. So I will explain granularity. This is our own novel contribution over. Then granulated regional based neural network, which is a very popular push-based tracker. Then I will take it as a case study our Tata Steel plant, real-time traffic anomaly detection. This is the last work of my last PhD from IIT Kharagpur, Onima Pramani. She has been now an assistant professor in Madurai, that Tata Institute of Management. And then finally, challenging issues if I get time. How much time? One. So what is granulation? So replacing a fine-grained universe by a cone-grained one, more in like with human beings. Just like I told you, I've seen in one, some old people, some young people, some lady. So this is my granule. So it's a process like self-organization, self-production, morphogenesis, Darwinian evolution, that are abstracted from natural phenomena. Basically, it is a natural computing. And the process that we generate, the clusters, segments, just like the old people, young people, some lady, they are called granules. So cluster segments are evolved by granulation. Granulation is the task, output is the granule. Therefore, granulation means it's a process of formation and representation of granules. And through information, abstraction and derivation of knowledge from data. Just in one slide, this is about granulation. Now, having a granulated domain, before that I go for this one, I say concept of granules then. Mathematically, what is it? It's a clump of indiscernible objects which you cannot discriminate with the given attributes. If you increase the number of attributes, they could be discernible. Just like in a data set. If you x-axis, y-axis, sometimes overlapping. If you add one more axis, then maybe some of them are discernible. So given some togetherness, similarity, proximity, functionality. For example, in genome data, you compute the similarity in terms of functionality. In the vector space, you compute the similarity in terms of proximity, distance. So classes of objects similar with respect to chosen representation of knowledge. So given a representation of knowledge as you define, and you see which of the data satisfy that property. That's why you form that. There are many ways of defining. I'm giving you example. Example of granule. Age. Very young, young, not so. So I do not go by the specific that age 10-year-old, 20 years or 25 or 23 or I got to say young, very young. These are my granule. Direction, when you drive a car, slightly left, slightly right, so on. School, every section is called a granule because it is determined either by age group, similar age, or by marks obtained in the previous class, or in terms of sex. So I call them as a granule. In image, they look at this image, there are 6 consecutive gray levels. According to Weber's law, our naked eye cannot discriminate. That is 1 to 6, 2 to 7, 3 to 8, I can consider as a granule because naked eye cannot discriminate. Now, if you take example, see that some of the granules have crisp boundary. Like here, here. But here, they don't have crisp boundary. Boundary is fuzzy. You can, everybody call young, it's a matter of degree. Everybody can go old, it's a matter of degree. Therefore, granules could be crisp, granules could be fuzzy. Clear? Now given a granulated domain. Before that, I go to a simple image. Image, it is a basically sinusoid. Because of the sinusoidal, you have got fuzziness. So you don't know where is the point. Now you do this discrete x-axis, y-axis, z-axis. 0 to 9 or 0 to say 31. 31 intensity. You create. You are losing information. Now, therefore, image is the best example of granularity. Image is the best example of because of the sinusoidal gradation of intensity, you cannot say which one is in the boundary, which one is not. Similarly, since you have discretized, we call it. And similarly, that is the lowest level of granularity. Now I can say find the similar intensity in terms of color. That will be another form of granularity. You can find the similar intensity in terms of color. That will be another. So that's how you can concept define granularity. That means you want to ignore the individual data. You want to extract out with respect to some knowledge, some. Now I have this granulated domain. And now having this granulated domain, before that I go. So then what will be the granular computing? It's a twofold task. Works with the process of information granulation, that is evolution of granules, and where computation performed using information granule, not the data, as I mentioned at the beginning. So since you are playing with compressed information, you are gaining computation time suitable for mining large data. That we thought in about 1.5 decades back. Therefore, in nutshell, granules evolved in the process of abstraction, derivation knowledge, and computing with granules of knowledge. Now, given a granulated data, So we can see that varying the size and shape of granules, you can determine different levels of granularity, characterize specific aspects of a problem. You can represent the model differently and regulate the decision-making task. That is, you from sparse to dense, if you go by the granulation, you have different kinds of results. That means my granules play a significant role. Now, giving a granulated domain, just like image, just like a school section, whatever thing, I define a concept set, crisp set. Given a granulated domain, I define a crisp set. Then how do we approximate it in terms of granule? So I can approximate from inside, outside, approximate from below or out. And that gives rise to the basic concept of graphs. So I have a granulated domain, I define a concept, region, whatever you think, it's a crisp. Now I want to approximate it in terms of that, because I don't have the concept of that, I have a concept of that. So when I approximate the set from inside and outer side, or inner side or outer side. And that description is called set. Next example, suppose this is my granulated domain. You can consider it an image, you can consider a school, different sections of different sizes. Now over this, there is x-axis, y-axis. If we add another z-axis, then the granule side will be reduced. So, and these are the granules means here, with respect to some relation xy, these points here, you cannot discriminate. So this is my granule. So given this granular set, I define a set, crisp set. Then I ask a question, what are the granules that will belong to this set? You see that there is no unique answer. Why? Because there are granules as marked by yellow, they definitely belong to this set. And there are also granules from outside, which includes this granule. They definitely as well as possibly belong. And therefore, I call it a lower approximation and it's called upper approximation. Lower means definitely belonging. Upper means definitely as well as possibly. Therefore, if I subtract from upper to lower, then I get this possible. And these are the granules, they create problem. They create uncertainty. So uncertainty arising from granularity is because of this. So if there is no roughness, there is no uncertainty. If there is no, if there is no granularity, there is no roughness. There is no uncertainty. So given this, similarly, in a school, some contaminated disease has been spread. So the principal of the school made a decision that infected classes should be declared holiday. Now the next question comes, how do you define infected classes? On one possibility that if all the students in a section are infected, so they have to be declared. This is called lower, about which you have no doubt. But there are some sections where not all the students, but at least one student was infected. Or then principal has to make a decision. They are like the check. That's on annual exam. There are many such examples of upset. So just to remember, lower is definitely possible below. And upper is definitely absolute. And in our all data analysis, that's the main thing. How to manage with the answer. How to manage with this answer. So roughness means 1 minus cardinality of lower divided by cardinality of upper. So cardinality of lower by upper, it will be less than 1. If cardinality of lower equal to upper, 1 minus 0. And cardinality of lower equal to will be upper when there is no granularity. So no granularity means no roughness. No roughness means no uncertainty. So the rough set, if you look at this, name is rough, but it's not a set is not rough. It's a crisp set, but with rough description. So this is the difference between fuzzy set and rough set. Because of fuzzy set, you can give thousands of examples. Say long street, large number, beautiful lady, blonde hair, etc. But in rough set, I cannot say because set is crisp, but with rough description because of this granularity. And this, Therefore, the roughness means basically it's a vague definition of the set in the universe in terms of lower and upper abstraction that signifies the incompleteness knowledge about you. Why incompleteness? Because of the granularity. So I will try to always minimize this incompleteness in order to make a decision. So minimize incompleteness to make. So I picked up the subject while I was working at NASA for 2.5 years because NASA, I do not know how many you, they not only do the research regarding space, but they also fund to university students, college students for just internship program, everything. So interns, East European scientists, they used to come for the internship. They used to give talk. They are very good in maths. So I used to learning from them. That's how I picked up the genetic algorithm also, because they are funding. So when NASA funds, means that subject is coming up. So that's how I picked the subject. That's how I see that when I listen, it's a two capabilities: uncertainty handling using lower and upper approximation, granular computing, and that granular computing term was not there, but the granular I remember. And uncertainty modeling I was using for fuzzy set theory, that we use membership function. We are using probability theory to manage uncertainty. And that time expert system was a buzzword. And there you see the many papers were coming using rough set theory for handling uncertainty in expert system. So before I go to uncertainty handling, yes, information granule, how you use and how you use this using lower and upper approximation for uncertainty handling in machine learning point of view. Today we have got the concept machine learning. In machine learning, we play with always cluster or concept, whether it is labeled or it is unlabeled, whether it's supervised or unsupervised. So given a granular domain, given a cluster, we can always think in a cluster, there is no ambiguity regarding any data points around the centroid. Ambiguity comes always from the boundary. Therefore, I can, in the notion of rough set theory, I can say this is my lower approximation, this is this plus 2 upper approximation. So given a cluster, I can concept the one in terms of lower and upper, and I can define roughness of the cluster equal to 1 minus lower and beta. And therefore, say now, but this is the definition of Professor Paula from Poland, land of mathematician. But we saw that he assumed both set and the granule are crisp. But we see in practice, both could be fuzzy. For example, in an image, boundary could be fuzzy because of this granule one. If you play with the 3x3 mask, 3x3 mask could be discrete, it could be overlapping. So in my practice, both of them, or at least one of them, and if one of them is fuzzy, the lower end approximation will be also just fuzzy. And fuzzy sets are nothing but membership functions. So if lower fuzzy set real life problem, membership function, so what we do then? You compute the summation of all membership values instead of counting the number of elements upper row. So that's why I compare the roughness of a just fuzzy set. So then it gives rise to concept of generalized rough set, when both of them are fuzzy or at least one of them fuzzy. And once a generalized rough set, there will be the classical rough set becoming just special case when both are crisp, both set and crisp are one. And it takes care of uncertainty due to overlapping concept, uncertainty arising from probability of occurrence of events. So generalized rough fuzzy entropy. Just one slide, very important, is highly cited. So if you take logarithmic gain function, say if probability of occurrence of an event is pi, that the amount of ignorance could be 1 divided by pi for the logarithmic Shannon's function. Or you can call it 1 minus pi also. So based on the logarithmic gain function, based on the exponential gain function, we have the similar kinds of entropy. And if you take the cross section, that means roughness of A and equal to roughness of B. That means if is the object, this is the background. Roughness of A and this complement set, we get this kind of selected, where roughness equal to A equal to B. So this entropy defines, basically quantifies the incompleteness of knowledge about the universe given the definition of the set X. Basically, it measures the gain in incompleteness. So my task will be always how to reduce the uncertainty so that incompleteness is minimized. Based on the simple concept, if we go back to 1983, when we didn't start this image segmentation problem. So object tracking from PBS, basically uh, video means sequence of object place, image place. So you want to extract the object from each image. That's actually simple set. So that what you can do, principle one, based what we did in 83 at Imperial College. Minimize entropy means minimizing uncertainty, that means minimizing incompleteness of knowledge, that means maximizing object background separation. And once you make object background separation, you can use it for object image segmentation. And then advanced person today for the last 30 decades, tracking moving objects in videos. Provided every frame has to have the correct segmentation. Now in a video, one additional feature, what is the temporal group? Time difference. In an image, only X and Y, intensity, nothing. If it's a color, RGB. But when a video, you have an additional temporal. If you subtract two videos, you get the moving objects because background gets narrowed. So second is making classification and estimation. So I will explain this last one, significance of granulation and lower upper approximation in unsupervised tracking of uncertain situation. Unsupervised, that means you do not know about anything, and it's an uncertain situation. But when you are tracking one object, suddenly another object comes. Objects are getting occluded, something like that. So what we will do, we use granules of arbitrary shape. That means you take an image, you start from pixel and start drawing with respect to spatial color similarity. That means you compute the distance, the similarity between two pixels and put a threshold, and if it doesn't exceed the threshold, you put the instant. That's how you do it. Just like if you start from here, old people I can grow one class, people, young people I can. So I use the two-dimensional spatial neighborhood. At arbitrary set, we ambiguous situation, and we define new concept of rough filter. Who are from electrical engineer, I have borrowed some concept from there. Granulated deep learning, I will explain that time. So this was based on US taking. I'm not going to rule-based classification, but all unsupervised. So what we do basically, you take an image frame T1 by T1, T minus T1, T minus T2, T minus 3. If you say 3 previously, if you can take 3, 5, 7, it should be odd number because you can compute the median value. So T minus 1, T minus 2, T minus 3, you take unit. T minus 1 to T minus 2, T minus 2, T minus 3, T minus 3, you get 3. So you get just the two concepts. So one you get one union, and we get 3. If actually there are previous frame, and use that neighborhood rough cell filter that gives the output of roughly estimate of location, color of the object in P frames in the next T plus 1 frame. So estimate from the 3 and T minus 1, you estimate the location of the object and color, direction at the T plus 1. Then you compute the roughness. If roughness is low, then you track the image. If roughness is high, that means objects are occluded. Then you compute the intrinsic entropy, which quantifies the amount of partial occlusion. Then you put those upper minus lower in this side and that side. You compute again roughness. You see which side is goes minimize roughness. Then you put in that one. So it handles partial total occlusion. So in electrical engineers, you have changed of information current to all previous frame. You have changed the information between consecutive frames. And you take the input-output relation. So you have 1 by P matrix. If you have done those filter, electrical engineer, Professor Panda is there. So you have 1 to P point convolution that takes care to result 2 P point matrix. One is called lower approximation, lower approximation. So your convolution operation is minimum and intersection and union. If you take intersection, you generate lower approximation. If you take union, out of those union, only to take those granules which have non-empty intersection with the lower. And that's how you generate the upper. Upper means definitely as well as possible. Lower means definitely. So if an example, you get this lower and upper approximation of each frame. So given T, you get the T minus 1th position, lower upper, T minus 2, T minus 3. And based on this, you compute the direction, change of color, change of velocity, everything. Then you estimate in the TA plus 1th frame. So now the performance, how do you compute? The signal to noise ratio of the filter. The lower approximation, upper minus lower approximation. Lower approximation means in cardinality amplitude, we should be higher because it's a definite belonging. Upper should be less. So therefore, low value of signal noise ratio is preferred. If you have high value, what you have to do? You have to reduce this and you have to reduce this also. So in order to reduce, you have to increase this and you have to reduce this. In order to increase this means you have to change the threshold value so that you get larger granules. Now see the result in London Metro underground. It's a 15 frames per second and P equal to 6, that means 5 previous frames. The complete occlusion, it can determine the complete occlusion. This is just one example. You will get many such examples in that paper. So you see the complete occlusion, I am making prediction basically. Prediction. I'm interested in the tracker. Now you see, so it's a one kind of machine learning. There are many such machine learning algorithms. It's a video is just an example. So it's similar concept you can for conceptualization video, remote sensing, microRNA ranking for cancer, because these are all big data. Neural network generation, social link prediction, air quality interpretation, everything. They are all big data. But when you do research, you have to think, where are they going to be applied for the next 5 to 7 years? Here comes the next question. You can use it for computer theory of perception, natural computing, and big data analytics. So what is CTP means? Computer theory of perception. That means you perform the computation based on the perception, not based on the computation. For example, when you drive a car, you use the perception of space, distance, speed, likelihood. You do not measure and then put your acceleration. You do not measure and then you round your steering. So that means, and because of this, our human brain has limited capability in resolution. Therefore, the perceptions are imprecise. That means their boundaries are fuzzy, and they accept attributes are granular. So that means the computer theory of perception, where you can use the F-granularity characteristics of computer theory perception to model. This is our next generation computer will be computation based on perception, not based on the measurement. And natural computing, because granular computing is a process like self-organization, reproduction, and Darwinian evolution that abstract from natural phenomena. And F-granulation is inherent in human thinking and reasoning process. Therefore, it is essential for human cognition. And next is big data handling. For any kind of large data, granular computing is required because uncertainty modeling and granular mining. Now, when you talk about big data handling, next question comes deep learning. It is inherent today. When we started working in 2010, we do not have that concept deep learning. Now it is a must. So, what is deep learning? In a layman's sense, learning in depth in different stages. Learning in depth in different stages. It is characterized mainly by learning the data representation rather than the task-specific application. Task-specific application means it is shallow learning. You give X, Y, X, Y, X, Y, and you ask the neural network to learn. But here we learn more towards the data representation. That's why we use so many filters. And today we have abundant data. Therefore, deep learning is a meaningful choice. But deep learning is time consuming, difficult to engineer because it has so many layers. Here comes the necessity of granulated deep learning. That means you reduce computation time, at the same time you try to improve the performance. Though you are compromising with the accuracy, you try to see how to improve the confidence out of the data. See, everything is inherent in the data. You don't listen. That's why the first said was important. That you don't just throw away. Once you make it two-step decision, then data is new. So try to keep as much as possible in terms of membership. So it is memory expensive. Now, let me show you convolution neural network. How many of you know convolution neural network, basic thing? Okay, I'm explaining one more thing. It basically says a neural network. You have a deep architecture suitable for image processing and video. It has convolved layer, max pool. So you are basically downsizing, and you are extracting more features. In object recognition deep learning means basically you label the different object regions in the image frame with their high probable classes and predict their bounding boxes. You take an object, you put a rectangle box. It is the convolution layer that is responsible to generate all kinds of features from the image. So basically CNN is a feature extractor. It's not a classifier. Up to this feature extractor. After that classifier, you can use any kind of classifier. So don't get confused. CNN is a feature extractor because convolution layer is responsible to generate all kinds of features using different kinds of filter. That's why I told you in the morning of our class, feature extraction. That time it was not important, but today is very important, feature extraction. Better the feature means better is the prediction, better is the classification. So DL-based object detector, for example, AlexNet, ResNet, there are many versions where you have multiple numbers of CNN and the max pool operation. It uses multiple CNNs as their backbone to extract features in depth for image frames and classify those with this feature. And using more convolutional layer extracts more in-depth feature. But adding more, it may not help because it's a question of problem of vanishing gradient. So you are going increasing, no, it will saturate. Just like in our 70s when we publish paper, you give the number of training sample, test is available. If you increase the number of samples after 70, 80, it doesn't change. Because it has certain limitation. Because it needs then another additional feature. So it's called, because if you work in the shallow learning, you'll see that when you changing the parameter is based on the gradient descent. So the gradient, when you increase the number of gradient of gradient, it doesn't change much. So it's called problem of vanishing gradient. So gradient responsible for training a network becomes smaller and more. So that's an alarming. So if you think that I put more, no. So you have to put it judicious. Just like in our shallow learning also, increasing number of nodes there, no good always. Because that affects the generalization capability. So having this, that was the CNN. Now my basic concept was we published in hello, please sit down. Do that. So how does it work? Suppose it is a 9x9 image. I mask a 3x3 mask. I scan it. Filter. 3x3 convolution mask with filter. I get the output y1, y2, I3. That means I will reduce from 9x9 to 3x3. So it's called convolved output. It's a dot product of WT and X. All the weighting filter has all this value 0.1, 0.3, 0 to within 0 to 1. I call it convolved output. So from 9x9, I have reduced to 3x3. Image size 1. This is so now here I have scanned, put the mask 9 times. Now suppose I put the granulation. That is, in the image I put granule segmentation. I get only say suppose 3 granules. So then what I do? I do not run here 3 times. I run only once and I copy. So instead of before I had y1, y2, y4. Now I get y1, y. So instead of 9, I only scan 3 times. Scan only 3 times, not 9 times. significant speed up, compromising some accuracy is called granulated CNN. That was the basic concept we published in 2018. That's basic concept. Now you play, how do you reduce more? How do you use granulation? What way granulation? That is your now problem. Now come to RCNN. It's a very popular for two-stage classifier. What is called two-stage classifier? You first, instead of segmenting or scanning from the raw, you first make an approximate location of the object what you want to detect, track. Then you make it fine so that you reduce computation time. So two-stage detector, object localization plus classification. So it first proposes or localizes approximate object region, then extract features from the object region by CNN, then followed by classification regression. That has nothing to do with the CNN. So what we do, we incorporate spatio-temporal. Since we are playing with the video, so why don't we take the spatial information? Sorry, temporal information also. I have the spatial information in image plane. Why don't I take the temporal information? So I take the spatial temporal information in forming granule. That means I do the computation only with pixels commonly lying in spatially segmented and just temporally segmented image. That means I am taking the lower approximation, which belongs both in spatial segmented image as well as both in A and temporally segmented. So that's how I am reducing the background. I am interested in background. I reduced it to only lower approximation. Now, by doing so, I might have lost some information. So then I put some rectangle 3 by 3, 1 by 3, so that if I lose something, I take it. Just like if you have a pure good student who doesn't know anything other than mathematics. So sometimes what you do, you put it into some bad student. Let him or learn some. Just like you have our pattern, you have a very pure data that cannot solve our real network. So inform the network, then we tell you some back, that is the boundaries. Then you make it integration. Similarly, the process part I believe only take those which belongs to spatially segmented, which belongs to temporal segmented. That means intersection. That means I lower approximation. Then I extend it. Therefore, it improves fast and faster RCNN, and the ROI region, the region of interest is smaller but effective. That means you gain in computation time as well as performance improves. Improves performance both during training and testing, improves real-time detection speed and accuracy. This is the so this is I take the Alex network, which has got 5 convolution layer, 3 pooling layer, and 3 fully connected network. I take the video F1, F2, F3. I have this video. I compute the spatial color granulation. The red boxes are our contribution, addition. We put the granule spatial color here, and all this temporal domain we get, and we get the temporal by 3-point estimation, background estimation. You can do it in many other ways. Then I take the intersection, so I get only these granules. It's called spatial temporal granules. Then again, after pulling, here again I take the intersection. So I am throwing away all background which I am not interested in, because they causes computational power and ambiguity also. And then I put some anchor. Since I might have lost something, so I put some anchor in different angles, 1 by 3 into 1 by 4 into 5. And those are my objects. And then I put them in the fully connected classification. So this is my feature extractor, etc. So as a result, what are the beauties? I take the entire video at a time, not frame by frame, as used to be by faster RCNN. I spatio-temporal granules by extracting region of interest is better than any, since I am taking spatial as well as temporal information. Other, they did not take temporal information. Only granules formed under 2 over 5 instead of entire map. And only empty regions corresponding to this granule we are taking for the classification. Therefore, it improves real-time detection speed and accuracy, both accuracy and speed. Let's take an example of traffic scenery. Traffic scenery is a common problem all in every country. Why? Because videos are real-time traffic scenario. They are small size objects, persons, vehicles, which are often noisy, unclear, occluded, low resolution cluster, because the camera is just put in a far, you're taking the picture. During seasonal changes, rainy seasons, foggy weather, you cannot see all these things. So until deep learning, what you to do in computer vision, you individually recognize each individual object and you track. But it is time consuming, and now you cannot make it clearly detection because it's foggy weather, occluded, scanty also sometimes data. So if you make inaccurate detection, your just tracking also will be inaccurate because success of the tracking depends on the accuracy of the detection. So our detection of this kind may not be accurate using traditional convolution computer vision technique till 10 years before. So, but on the other hand, today we have big data. That means on the same road, I have got data for last 6 months in different seasons. So why don't I train the entire data instead of individual objects? I put everything in the data. That's why in the morning someone said, no, I'm not going for the individual data. I'm thinking. I'm taking the entire data because that's the advantage I have. All those data in the same street for last 6 months, last 1 year, 2 years, and different time seasons. I take entire data, I put it. So abundant data on similar situation. Therefore, relevance of deep learning. Because you may ask me question, why are you go for deep learning? Because conventional machine learning, conventional computer vision cannot solve this problem, because if your detection of human is not good or detection of the object is not good, the tracking will not be good. Therefore, your surveillance problem will be affected. So let me appear with this our Jamshedpur steel plant data. About 2K video we use. There are 8 objects like car, bus, loco, truck, minivan. These are put in one class. Bike, scooter, bicycle, person. GPU 650 was used. 84 frames for using Fastara algorithm, which is a widely. See the thing I'm taking the blocks. Yes? 3 types of blocks. Bounding box. Green, pink, and the person is in the blue. You can see that some of the pixels, some of the objects, some of the frames, they could not identify. I'm showing again. And it has detection speed in 6 frames, tracking speed in 29 frames. Tracking speed in 29 frames, but for visual, we have reduced it to 10 frames so that you can locate it. I'm showing it again. If you minutely look at that, in some frames, some of the objects are not being able to be detected. Now I next go to that spatio color granulation with spatio color RPN. Now there are some red circles, means those are the objects which could not be detected earlier. See red circles coming because those are the objects which could not be detected previously. Because of the spatial color you are getting, but here the detection speed has reduced to 5.5 because you are extracting some information. Now you go to spatial color temporal. That shows further some red circles which you cannot detect using the even spatial information. So your accuracy is improved a big manner, both in terms of mean accuracy precision as well as by speed. And speed from the spatial and spatio-temporal, it has improved by 5.6 for 5.5. You remember that In case of spatiotemporal, I use an intersection operation. So instead of additional operation, it has reduced because why? Here the number of granules is less, but they are effective. Effective. So now, in short, GDL enables more accurate localization, detection, and prediction. More accurate localization because it's a two-stage localization, detection and prediction. So it has got enormous application in shipbuilders and other. IIT Kharagpur has a very big project of the garden reach, how to pinpoint some repairing in a ship because of the localization. Now, next question I'll show. Based on this, you say fault detection. Fault detection is a very important system, whether indoor fall or outdoor fall, particularly for the old people. Fault detection indoor is a very challenging task now. I will show in our steel plant this fault detection system where we use the same network we have used for detecting the object first. We put the label and use object level features like change in area, aspect, change in speed, change in direction. These are all additional contribution. And we use 18 open pose filter which are available in the market. The open pose filter is a neural network that extracts two-dimensional location of eyes, ears, nose, neck, etc. So if you look at this fault detection, very carefully this heat. In Jamshedpur steel plant, see the thing fall. The guy fell out. Again, I'm showing just one slide on. If you use similar CNN-based others, their accuracy is not there. Only 93.5 or 5 feature, but here it is 11 processing speed 11 frames per second, and accuracy is 99.63. And if you compare to similar state-of-the-art one, the processing speed is 9, 10, 7, 6, and the accuracy speed also 93.5, 95, and 98. That was the first thing. Now, next one I'll show is advanced person is available in this. Now, another important is the traffic anomaly detection. That means anomaly between collision and near miss. Collision in and near miss. There we use the question of explainability also. So first of all, I'll explain why do we do it near miss. It's appeared in ITP transitional intelligent transport system. So here we use 3 types of granule. First granule is in terms of change in displacement speed. Second granule is change in neighborhood object distance. Third granule is in terms of intersection between 2 objects, change in intersection. So in case of normal, we do not want to change C mass in case of normal traffic. If there is an abrupt change, then we will get an accident or anomaly. So basic thing is that. So we have 3 types of granule. So less change in position, neighborhood distance, and IOU, intersection of union of an object, is desirable for normal scenario. So the scenario could be, so every object represented by its centroid, it will be characterized by membership value to 3 types of this granule. So in case of correctly detected and tracked object, all these granules will be for membership value close to 1. That means there is no change. That means green, these are marked by green bounding box. So when I say green bounding box means they are perfectly okay. There is no question of accident or collision. Now, second procedure in case of collision, centroid of the constant granule will have 0 or 1 for all the 3 granules. All the 3 granules, there will be 0. That means there is an abrupt change in distance, abrupt change in neighborhood distance, abrupt change in the IO. Similarly, another is near miss, that we consider that at most 2 out of the 3 will have 0. Just this basic, accordingly from the rule. See the collision is still plenty. Green miss, no problem. Other 3 colors, yellow, red sea, and blue, their appearance means their values are 0, closing to 0. Values be closing to 0. See, there is a collision. So that's why all these three collision. Collision with the Z values certainly, that is the explainable. Certainly. Similarly, I call to the near miss. Green means no problem. One green means one of the granules is 0, no problem. But the two granules are 0, it's near miss. Not the green one. Here it is a near miss coming. Near miss. That means the guy was about to fall. He has ladies. Seeing again. Certainly. Near miss. This portion, you look at this. The scooter was about to fall. So the thing, it is indicated by this at least two granules near sea blue and the real blue. And here also G number indicates the certainty, because there are four kinds of certainly, not so certainly, likely, unlikely. So now the next question comes, how to quantify this measure, certainty. So here you use the concept of G numbers. There is a very new concept, G numbers. G number has two tuples for any events, safety analytics. We have been using with IIT Kharagpur also. It represents the real value to when there is a fall. When you think it, when you have the data, uncertainty in the data, we have managed with granular computing. Instead of considering individual point, we are considering the granular asset together. Whenever we cannot segregate two elements, we consider two together. But in the output decision also question arises, how do you say it is near miss? How do you say it is a collision to just what extent? That's what we are doing here, using the concept of Z number. It's a two tuple. H represents the real valued uncertain variable, and it defines the reliability of this H. Two. So for every event anomaly, whether it is a collision or one, we compute G numbers with respect to collision, with respect to nearness. So how do you compute? We compute the roughness score with respect to anomaly. Roughness score for collision, roughness score for G number. Roughness score means you take this value of H and the E and they are multiplied and they are squared, roughness score. That is give the composition. And then what is interesting value? It is with respect to the anomaly denotes. I'm not going to the detail now. Just I'm giving the one abstract concept. It denotes the, with every anomaly has a interesting value, that is reliability, which denotes the membership value of this lower approximation, because eta value is the membership value of the lower approximation, it will definitely belonging. So membership value of the lower approximation certainly belonging to that anomaly. So you have the lower approximation, but what is the degree of certainty to belonging to that anomaly only? So lower eta value is desirable. Now you see that from frame to 100, which I'm keeping some sample value. From up to this you see Z value of this collision, age and roughness, collision. You look at this, every value here, age values and E values are much less than here. Therefore, we say that these R and lower values are lower. That means here collision has occurred, not the, see, collision and near miss, there is a fuzzy term basically. About to near miss, about to collide. This is just basically a fuzzy term. So that's why you are indicating this way. This is one way of indication. So collision has occurred in frames 98 to 95, and this collision event, we call it most likely collision, because it reliability value is 0.2. So I put 0 to 0.2 is a certainly, 0.2 to 2.5 on the H value is called most likely, the least likely, and such as 6 division. So this gives a quantification of, or this explainability why this is called your collision, not the near miss, or the near miss, not the collision. So up to this now, one thing here, whatever I have done, it's a granular level processing. I didn't do granular level decision. So you can think of granular level decision making. That means, should we go by the finer granule or we just go by the coarse granule? That is, whatever decision that we read, how much accurate we need it. That's how you can make it coarse granule, or you can make it finer granule. Finer granule always needs some more money. So that you can think of that way. So, and the evolution, as I mentioned before, at some time. So see, pattern recognition started in 1960s, but in India we started in 70s. In my knowledge, at TIFR, Institute of Science and my institute. The US processing started in 1970s. When I went to Imperial College 79, we started there, but in Professor Rosenfeld group in Maryland, she had started, and here also our defense lab, they started when that was in also late 70s. The AI ML expert system, they came in 1980s. Just around 10, they are all a buzzword at that time. And knowledge-based system 1990s, data mining 2000, because of the data. Big data 2010, now we are calling it data-driven. Science and one, after 10 years ago. Now everything is still there. For every time it's evolved, there is a new terms and coined, new terms, new technologies to cater to the need. For example, when we started feature selection problem in 75, 77, we have 2 to 3 features of speech. Out of those we have seen, and the number of samples was larger, about 1,000 samples. We have seen which are the features responsible for greater separability. That's how we published in ITP transactions that time. But after 80s, you cannot publish that paper. Their name is that we call feature selection, now we call it diversity reduction. That time we used to call it classification, now we call it a retrieval. That time we were going to call it a subset selection, now we call it a data condensation. So new names are coming up which are user-friendly basically. But it's the same concept. So if you look at when we, 2000, when we say data has a large sample, say genome data, or it's a medical system. When you go to a medical doctor, you tell your problems, you have their all pathological information, you have the family background, these, but they do not think that in machine learning guy will use this data. But machine learning guy have no other duty but to publish, so they get this data. So then they see that they cannot classify based on this, which is normal and cancerous, because data is heterogeneous and feature is a large number of features. Similarly, in gene selection, it's a few thousand genes, but the class is only 2 classes problem. So entire thing becomes changed. So you cannot publish what you cannot use what you published in before 80s. They are no more useful because of the data. So that's how we publish in a very highly cited paper that you have a data features are uncorrelated. So instead of clustering in the sample space what we did in 70s, you cluster in the feature space. Since features are uncorrelated, they will be clustered. And since you have a cluster, so if you have a few thousand samples, features, and if you can reduce it to few hundreds clusters, then pick up the centroid of the cluster, and then that will represent the features. So for a few thousand, you can reduce to one. It's beautiful. So that's what we published it. So new terms and technology coined, big hope, but it's a caution. Don't jump into the subject. That's why I mean it. If you want to learn deep learning, you have to learn shallow learning. You have to learn shallow learning. You have to learn neural networks. If you learn neural networks, you have to learn pattern. If you want to video, you have to know image processing. Basic concept of segmentation, enhancement, edge detection, feature extraction. Segmentation is unsupervised. Now everything is also. That's why clustering becomes so important. When we started working in clustering, that was a subject of all electrical engineering. But today it is subject for anybody. whether mathematician, astrologist, whoever having some data. If you do not know anything about data, what do you do? You try to cluster. How do you cluster? You don't know numbers. Okay, let's consider C equal to 2. You see whether there is a homogeneous packet. Let us see C equal to 3. C means clustering. So you make it. So at least you get some idea where from you can start. So this one I conclude on a separate note. It's my personal opinion. Any excessive talk in any topic by ignoring the growth of other disciplines may sometimes be no good. It affects the progress of the overall science, which is responsible to maximally benefit the society. With this one, I acknowledge my students and young, because I have worked throughout my career, mostly with the younger colleagues in India and abroad. Not many big professors. National Science Chair, who is now still holding. Thank you. Thank you very much. I tried to explain this advanced topic as a multidisciplinary as much as lucidly as just possible. So if you have any question. No,
I 3-2 you told highly likely.
No. I understand that. I understand. Yes, no, it should be higher. But here, the way we have computed n, that means it's a we are considering. See, we are.
Somewhere the negation is there. That's what I feel.
No. This one. When I say it's a normal country, that means membership value is what? There is no change in distance, no change in neighborhood distance. When there is a
I just want to draw your attention to the last line. The event is most likely collision with reliability 0.34.
Point 0.34 means height words.
Yeah. So
Height.
suppose if the number was 0.8.
But no. Let's see
So,
the thing.
Okay, I don't know. You are getting my confusion or not.
No. I know you know your confusion. If you have missed my membership value 1 means normal.
I just want to look at one statement. If it is reliability,
No.
1 is most reliable or less reliable? That you tell me.
No. Here it is just less value is desirable. You see, 0.02 certainly,
okay.
0.25 to most likely. If you go to 6 here, less likely. That's
how you have defined.
Defined because we say the lower L value is desirable. Lower eta value is why is it desirable? Just looking at this value.
But then you should put unreliable.
No. Just a minute. See, granule is formed such that changing information is below threshold. Granule 2 is formed changing values.
Okay, that is your definition. I agree with you.
No. Just a minute. Here is the thing. Correctly detected means membership value towards 1. So I am not bothering about this. Only case of collision, all values are going to 0. And I am considering on near miss, 2 of the values will be going to 0. Understand? So therefore, since I am concerning with collision and near miss, not this. So therefore, lower the value means more just this.
Okay, thank you.
Yeah, otherwise, if you see that no, it have value, that's why I mentioned that it's the lower value is desirable. Because the definition from this one, in terms of granule. But anyway, the basic thing is that it is that network, it is good for localization, detection, and real-time prediction. Therefore, that you can use for any kind of object detection related problem. Whether it is a human-driven car, or it is a IoT, or it is any the health-related problem tracking somebody. because you are perfectly localizing, perfectly detecting, perfectly you're predicting. Three things you keep in mind. This fault detection, other things, there is one example towards just safety analytics. But you can put for many others. With object detection, if you have a good detector, all applications, whatever is seeing are objects, basically. Whatever you see, most of the scene is a visible object.
I'll just come. Hello. In conventional CNN,
Yeah.
please listen.
Conventional CNN. I'm just coming back.
Yeah.
Conventional CNN.
In conventional CNN, after stages of convolution, features are extracted.
Extracted. Just a minute. Yeah. Conversion situation.
Listen, I'm not told. Features are extracted.
Extracted.
Features conventional. Features are passed to classifier or detector or forecaster.
Cluster.
Two stages. Now in this granular deep learning model,
Same.
feature selection and feature reduction, are they practicing?
No.
Is it introduced?
Same.
Before it is fed to the classifier.
No, same.
Feature selection or reduction is done on.
No. Here also you see in the conventional classifier, you extract features,
Okay.
then you reduce, max pool, ReLU, then
No, here it is not so. Here, feature selection, feature reduction are very important to reduce complexity.
No.
Here in this diagram, it is not.
No. This is conventional CNN. You are extracting feature. You are just putting some filter. You are reducing the feature. Basically, up to this, you are extracting feature that you put to a fully connected network, fully connected classifier. That's why I said classifier. You can put any kind of classifier instead of support vector machine. You can put it into KNN classifier. It's basically a feature extractor. Basically, convolutional network is basically a feature extractor. That's what I told you, first of all. Same thing, I'm also doing, in case of granulated also, I'm extracting features out of this. So, that's how I reduce computation time. Now, in case of RCNN, there is a two-stage classifier. RCNN. I'm just coming to the feature. RCNN, basically, if I remove this, it's the same convolution. There are 5 convolution layer, 3 pooling layer, and 3 FCL layer. Just simple. So here is a two-state classifier. Even in the RCNN, you make first localization of the object approximately. Then out of this, you extract features, further features, which will be fed to the classifier. So this is, it is called GLXNet. It is called proposing network. It's called proposing network. Proposing means you are localizing object feature. So basically, feature extractor. And out of the feature extractor, you are further reducing to make it accurate which feature will be taken, that is extraction. Then you put it back to one. I am also doing the same thing, but I am modifying it.
We'll discuss. We'll discuss. Second thing, for my information, in CNN, you perform convolution 3 by 3 or 5 by 5, stage wise convolution. You perform. That convolution takes time. Your approach will reduce the time. Okay? But there are some types of faster convolution, rectangular transform.
Yes.
Slantlet transform. 30 times faster.
Faster. They are also.
My question is, if those transforms are introduced instead of conventional convolution, total time of this approach and this new fast convolution based CNN Which one will be better?
No, I'm coming. My concept is given anything, I put it granulation concept, I make it just further economic, and I'm just more happy. So whatever you give me, I put my concept there, granulation, and I reduce further the background for this kind of object extraction. I'm not talking of other, because here I'm not interested in the background. You look at it. Basically, I'm making selective search. Instead of basically, I'm making selective search.
Let's see.
No. See, conventionally or whatever you give, there are different variants. But I can use further concept of granulation. Since I'm using the image, video, I can reduce that further. And I can get more accurate value. That's the beauty. See here, conventional layer is just background. You can use any kind of convention which are advanced. No problem. No problem. But still I can use the basic concept of granulation on the image domain and equoroporia so that I get better object detection problem. That's, if you give me that, I will just improve it further. If you give me another one, I will just improve it further. Understand? Basic concept is how granulation incorporating, helping.
I think we know grad transform.
No, maybe. Single
That is
person.
50 times faster.
No.
So we have to see this approach and this other approach.
No, obviously. See, publication. See, publishing one paper is not actually just solving all the problem. It is just an idea given. Great. Now, see, when you publish in 18 and now when you publish in 2002, 2003, they are still publishing because we are giving new idea. Concept is granulation. Simple. That instead of considering individual, you take as a property as a.
We'll discuss.
Thank you. Anything else? Thank you. Thank you. Thank you.
Esteemed Professor Dr. Shankar K. Pal, esteemed dignitaries of the dais, distinguished guests, organizing committee, and dear participants. At the outset, on behalf of the organizing committee, I extend our heartfelt gratitude to Professor Dr. Shankar K. Pal for gracing us with his presence and sharing such profound insights with us today. Your words have truly enlightened us and provided deep perspectives that will inspire our academic and professional pursuits for years to come. We are immensely grateful for the time and wisdom you have shared. I also take this opportunity to sincerely thank all our dignitaries, Professor Dr. Ganapati Panda, Professor Ashok Kumar Tripathi, Shri H.K. Ratha, Shri Preet Yadav, Professor Srinivasa Sastri, for their kind presence and continuous encouragement. Your support has added immense value and prestige to this conference. With that, I once again thank Professor Pal and all dignitaries for making this session a memorable one. Thank you all.